In my previous video, we looked at the basics of electric fields. We looked at what a field is. Again, we looked at what an electric field is specifically. We looked at what we mean by electric field strength. We looked at the field patterns around isolated charges, both positive and negative. We looked at the field patterns around two charges near each other, both positive, both negative, and one positive and one negative. We looked at the difference between uniform and radial fields, and we talked about how gravitational fields can never be truly uniform, although they approximate to being uniform near the surface of the mass. And you do have genuinely uniform electric fields. So let's then put some maths around field strength. So Coulombs' law is very similar in structure to Newton's universal law of gravitation. And Coulombs' law says the force between two charges is proportional to the product of the charges and inversely proportional to the square of the distance between centres. Now, if we're talking about point charges, that last bit doesn't really matter. So what we have is the force between our two charges is proportional to the product of the charges, let's call them Q1, Q2, and inversely proportional to the square of the distance between them, which of course takes us, this being a proportional relationship, if we want to make it an equation, then we need a constant of proportionality, K, Q1, Q2 over R squared, and K is 1 over 4 pi epsilon naught, where epsilon naught is the permittivity of free space or a vacuum, and it is 8.85 times 10 to the minus 12 farads per meter. Now, don't worry about the farads because that's a unit we'll come across when we do capacitors, which we will do after we've done electric fields. But notice the size of the constant here, 1 over 4 pi times this. That's going to give you something like 9 times 10 to the 9. Compare that to the constant in gravitational fields. 6.67 times 10 to the minus 11 is the magnitude. So the force between two unit charges 1 meter apart and the force between two unit masses 1 meter apart are very, very different, in the order of 10 to the 20 times different. So there's one of your differences with electric and gravitational fields. Gravitational fields are very, very weak in comparison. So let's just put our Coulombs law down formally in maths. So the Coulombs law says F equals 1 over 4 pi epsilon naught Q1 Q2 over R squared. There's your maths. Oops. Which, if we then go on to say, well, that gives us the expression for the force between two charges, what about the field strength around a charge? Well, the field strength, of course, is defined as the force on +1 coulombs. So if I set one of my charges here to being 1 coulomb, then I get a field strength expression in a radial field, remember, of 1 over 4 pi epsilon naught Q over R squared. So there's our field strength expression, which just comes from our force expression and setting one of those to be our test charge plus 1 coulombs. So you can see if this is positive and this is positive, this will be positive, repulsive. If this is negative and this is negative, well, minus times minus gives you plus. So a positive force is a repulsive force. If they're positive and negative, they'll be attractive. So anytime you see a positive force, that's repulsive. Negative force is attractive. So there you have your expression for the force between two isolated charges, or two spherical charges, if you like, near each other, a distance r apart. Here you have the field strength at a distance r from a charge q, coulombs. Those are your expressions for field strength in a radial field. Let's look then at a uniform field. Here's a diagram you've seen before. So here we have our two plates with a potential difference of V volts between them, and they are distance d apart. So our field strength here, using the same symbol as before, field strength, is V divided by d. And that, of course, the units of that, volts per meter. And you'll remember that we talked about field strength being the force on unit charge. So field strength is newtons per coulomb, and you say to yourself, well, how can that be? How can volts per meter and newtons per coulomb be the same? Well, you should do a little exercise to verify that volts per meter and newtons per coulomb are the same. Have a go at that. Pause the video, have a go at that, and then see what you come up with. Coming back to that then, well, volts, we know volts are, 1 volt is the energy, the work done in moving 1 coulomb plus 1 coulombs between 2 points in a circuit. Hopefully you know that. So if we make that joules per coulomb per meter, we know 1 joule is the work done when a force of 1 Newton moves its point of application through a distance of 1 meter. So the meters will cancel. We've got newtons per coulomb. So there you go. So you have two expressions then for field strength. You have one for your uniform field here, and the other for your radial field. Make sure you're using the right expression for the right kind of field.